Let's talk next briefly about prefixes in the metric system and also SI units and what those are. So you're hopefully familiar a little bit with metric system, having seen it before, and you'll notice that there are a large number of prefixes that then determine the size of a number. And we can start all the way at penta being 10 to the 15th power, which means one with 15 zeros after it, all the way down to zepto, which is 10 to the minus 21, or 20 zeros in front of a decimal point and then 20 zeros in front of 1. But many of those prefixes you may not be super familiar with. I will highlight just the prefixes that we will mostly focus on in this course that are used the most frequently. So the kilo down to nano are the most common. Let's go through that in just a little bit more detail. So for the metric system, essentially each prefix is, there's a prefix for each unit of 10. The metric system is based on units of 10. And if we start here with the base unit, whatever that base unit happens to be, could be maybe a gram, or could be or it could be a liter, or some other thing like that. But we'll start with the base unit. If we add a prefix in front of it, that will tell me something about the number of base units that make up the new unit that has the prefix in front of it. So for example, if I've got kilo, that means I have 1,000 of the base units. Deca means I have 10 of the base units. If I go down here to centi, that means I have 1/100th or 0.01 of number of base units in that presence. So that means, so deci, centi, milli, micro, nano, those are all units that are smaller than the base unit. They're all factors of 10 smaller. So milli is 1/1000th or 0.001 number of base units in that unit. Let's go through a specific example. So kilograms, decagrams, grams is going to be the base unit here. So we're talking about mass. Gram is my base unit. And if I look at this and say, well, 1 kilogram is 1,000 of my base units, so it's 1,000 grams. There are 1,000 grams in a kilogram, whereas there are only 0.01 grams in a centigram. So a centigram is 1/100th or 0.01 of a gram. A nanogram is 1 times 10 to the minus 9. There are essentially 0.000000001 grams in 1 nanogram. Just to list a few unit relationships here within this. So we've got abbreviations for each of these, and the abbreviation for gram is just G. So 1 kilogram is equal to 1,000 grams, all the way down to 1 nanogram is equal to 1 times 10 to the minus 9 grams. These are relationships that you must know to proceed. We really need to be familiar with how the metric system works and the relationships between units for any of what we do going forward to make sense, since all of chemistry is primarily based on the metric system. Now, the metric system we just talked about, the example I used was grams. But additionally, there are units for all different types of measurement, whether it's mass or length or time. And to limit confusion, scientists have gotten together and decided on one set of units to be the standard unit for which to reference everything by. And that helps for it helps provide some uniformity amidst the kind of variety of units that people had previously been reporting. And so these are the standard international units for particular measurements. And then we'll talk about some deviations from that. So mass, the standard unit is actually the kilogram. This is one of the few where the standard unit is not the base unit. Base unit is a gram, but the standard unit for mass is a kilogram. For length is a meter time a second. And temperature, the standard unit is Kelvin, which we'll talk about a little bit more. And the amount of substance is also a mole. We'll talk about that more in chapter 3. Now we also have electric current and luminous intensity, but to be honest, we won't encounter those in this course. So we will leave those kind of off here a little bit and focus primarily on the first 5. So those are the standard base units, and all other standard units for things like volume, for example, are derived from these 7 base units. So let's go through a few examples. First, let's talk about temperature scales. The standard unit is Kelvin. Well, what exactly is Kelvin? Since we're mostly familiar not with the Kelvin scale, but with this Fahrenheit scale here in America, and we may be a little bit familiar with the Celsius scale. Well, all 3 are temperature scales that all measure the same. Of course, they measure the same temperatures and report it, though, based off of slightly different scales. So we're familiar mostly with the Fahrenheit scale, which runs primarily between 32 degrees and 212 is the primary range on an average day, even during the winter, although the winter will sometimes dip below 32. And mostly this is all referenced here to the temperatures that water boils at and the temperatures that water freezes at. And the Celsius scale has been set to make those temperatures be uniform. So water boils at 100 and water freezes at 0. But both the Fahrenheit and the Celsius scale have the possibility for negative numbers. It's actually quite common in the winter to have negative temperatures in the Fahrenheit, and certainly any temperature below the freezing point of water in Celsius is negative. But this complicates calculations that would use temperature, because if we suddenly have a negative number, that will throw all of the numbers off. And so what we need is an absolute temperature scale where there is no negative, where 0 is the lowest possible temperature ever, and that is the Kelvin scale. So Kelvin is referenced not based off of the boiling temperature of water, but 0 Kelvin is actually absolute 0, where all molecular motion stops, and it is not possible to have a negative value in Kelvin. Now, the conversion between these 3 scales is actually relatively simple. Kelvin is just the Celsius temperature scale with 273.15 degrees added. That makes sure that we never go below 0. And then the conversions between Celsius and Fahrenheit are also listed here. Fairly straightforward. If you have a temperature in Fahrenheit you want to convert to Celsius, you simply subtract 32 from that value first, and then multiply by 5/9, which is essentially the conversion for 1 degree between the 2 scales. And then you can simply rearrange this equation to solve for Fahrenheit. If you know a temperature in Celsius, you simply take that value, multiply it by 9/5 first, and then add 32. So those are temperature scales. Now, what about derived units? It's said that all standard units could be derived from the 7 base SI units. Well, volume is an example of a derived unit. So volume is measured, if we show a cube here, if we were using the standard units for length, you would have a volume that was paced out by 1 meter, 1 meter, and then 1 meter in height. And that would give you then your derived unit for volume as being the meter cubed. That is the SI unit for volume. However, 1 meter cubed is a ginormous volume. We certainly don't talk about meters cubed of milk or gasoline even. And so if we take just one small section of the meter, if we take 1/10 of a meter, that would be a decimeter, and we do 1 decimeter by 1 decimeter by 1 decimeter, that now is a much more reasonable volume, and we actually set that equal to something that's known as the liter. So 1 liter is a metric unit that is equal to 1 decimeter cubed. Now, even 1 liter is often too large for a volume to be useful. We don't talk about dispensing medical dosage in cubic decimeters or in liters generally, unless it's saline solution. So 1/10 of a decimeter, which is 1/100th of a meter, is a centimeter. And 1 centimeter cubed, 1 centimeter by 1 centimeter by 1 centimeter in height, is the milliliter. And that is the more common. Milliliters, or sometimes liters, are by far the more common units. They are not the SI units, but they are the more common units for volume. So those are units you should be aware of. Additionally, density is a derived unit. What is density? Density is the ratio of mass of an object to its volume. So if we take the standard SI units, for mass, it's the kilogram. For volume, that's meters cubed. So the SI unit for density is the kilogram per meter cubed. And you will see this commonly if you look up densities. You can find densities reported as kilograms per meter cubed. But if we were measuring, for example, the density of some object, let's say I wanted to measure the density of water, to get 1 cubic meter of water would be difficult. And even if I did have 1 cubic meter of water, I don't have a scale that would easily be able to measure that size to be able to report the mass in kilograms. So what's much more common is the gram per centimeter cubed. This is a much more common unit for density because it's much more easy to measure. Centimeters cubed, remember, is a milliliter. I can easily measure a milliliter using like a graduated cylinder. And grams, I can easily measure out a gram worth of material on a scale. That's quite easy to do. And so we should be aware that the conversion between kilograms per meter cubed to grams per centimeter cubed is that 1 kilogram per meter cubed is equal to 0.001 grams per centimeter cubed. This is by far the more common, and here's just some examples of densities for common substances. Air, for example, has a very low density. So this would be 0.001 grams per centimeter cubed. But something like water has a density of 1 gram per centimeter cubed. Gold is certainly much more dense at 19.32 grams per centimeter cubed. And you'll often see units reported as grams per milliliter as opposed to grams per centimeter cubed because milliliters and centimeters cubed are the same thing.